Hello students, in this video we'll discuss the geometry of LFTs. We'll show linear fractional transformations can be expressed as a composition of a translation, a dilation, and an inversion. Okay? So let's recall that an LFT is a mapping of the Riemann sphere, is a mapping of the form T of Z is equal to AZ plus B over CZ plus D, okay? And so what I want to do is I want to introduce a couple different transformations of the complex plane. So let's do that. So what are some transformations? The first one we're going to do is translation, right? So translation is a very easy operation in the complex plane to see, right? So I'll call this mapping over here T1. Let's call this over here. Sure, let's actually change the name of this LFT. Let's call this thing over here. Let's call this thing over here S of Z. Okay, so I can use T for something else, okay? So translation as a function of Z, translation by a point A is just gonna be the mapping Z plus A, right? And so all that's gonna do is that's just gonna take every vector and translate it along the direction A. So we're just translating along A. Translate along the direction of A. Okay, good. And now one thing I'm gonna make a silly observation. If I take a line in the complex plane and I translate it, it stays a line. If I make a circle in the complex plane and I translate it, it's still a circle. So lines go to lines, lines and circles get mapped to lines and circles. Great, that's easy. All right, and so what's the next operation we're going to talk about? We'll talk about dilation. So the next one is dilation. Complex dilation, of course, right? So dilation via lambda of Z is going to be what? It's just going to be lambda times Z, okay? Now dilation does two things in the complex plane. In the complex plane, dilation scales by modulus of lambda and rotates by argument of lambda. So it scales by modulus of lambda and rotates by arg of lambda. Okay, good. All right, and so now what's the idea? So the idea now is that you say, okay, well, what happens to lines and circles? Lines and circles go to what? If you take a line and you dilate it, stretching out the line has no effect on it. Rotating the line preserves its linear structure, right? So in other words, a line gets mapped to a line. What about a circle? You're going to take the circle and you're going to dilate it, make the radius bigger, and then rotate the circle. Rotation doesn't change the circle, but dilation makes it just a bigger circle, right? So lines and circles go to lines and circles. Okay, good. All right, and then what's the next one to do? Inversion. Inversion's a fun one. Translation, dilation, inversion. So right now you're thinking of sort of like the rigid motion you did in Euclidean geometry, right? At some point we'll get around to my version of my version of Euclidean geometry, right? I don't want to spook off viewers too quickly. The whole point is that Euclidean geometry is very beautiful. I think that oftentimes in the US we've just basically let it go off the rails. And the geometry books are like statement and reason, just write sentences and then just sort of do it as Euclid did. It's much easier. We'll get to that playlist eventually, right? So that's something to look forward to. Okay, what's and we'll talk about inversion a lot when we do that, right? Because inversion is a very important idea. Like circle inversion is a very important idea in geometry and projective spaces, okay? So what's inversion? I will call it I of Z. I of Z is just 1 over Z. Okay, and what does inversion do? They might say, oh, that's just sort of similar to circle inversion, right? But almost, right? Inversion over the unit circle, here's a note. Inversion over the unit circle, we're going to see that, we'll do another video on that too. Inversion over the unit circle is given by, is Z gets sent to 1 over Z bar, right? Because remember that when you do an inversion, what happens over here? So if I look at if I just looked at 1 over r e to the I theta, that's just 1 over r, inversion of the circle, the radius, then e to the minus I theta, right? So in other words, what have you done over here? When you do ordinary inversion doesn't necessarily does a reflection over the real axis, right? So if you wanted to make it a inversion over the unit circle, you have to put a bar over here. But we don't want to deal with bars because those are not holomorphic functions. This is a holomorphic function, okay? So we have those 3 transformations. But I claim I can write these LFTs S as a combination of these mappings over here. So let's do that. So claim, and this is one of the most common exercises in complex analysis. Here's a proposition. So we'll simplify it dramatically. Proposition. The proposition is that any LFT can be written as a composition of these, and these are also what? All 3 of these things are LFTs, right? As a composition of these 3 mappings: translation, dilation, and inversion. Okay, that's the statement. Okay, so here's the proof, right? The proof is straightforward. So I'm going to do a simple case first. The simple case is if c is equal to 0, right? So if c is equal to 0, then what does s look like? Then s looks like s of z is a over d, and then also that d is, now if c is equal to 0, d can't be 0, because recall that AD cannot be equal to BC, right? So if c is equal to 0, I cannot have d being equal to 0 also, right? So d is not 0 in that case. AZ like that, and then plus b over d, right? Plus b over d. Okay, good. All right, and so of course this is just a complex, that's just a what? That's just a complex number, and that's just another complex number, right? So this is really just what? This is really just a tilde z plus b tilde. They're linear functions. And so what I'll do is I'll first dilate. So this is really what? This is going to be, I'm first going to, I'm going to do dilation by a tilde, and then I'm going to hit that with a what? With a translation by b tilde over a tilde. Translation by b tilde over a tilde of z. What will this be? This will be dilation of a tilde, and then what? And then then a z plus b tilde over a tilde, right? And then if I multiply a tilde, I get a tilde z plus b tilde, right? So that's the first case. The case when c is equal to 0, then your linear function, and linear functions, this may be more confounded than need to be, are clearly compositions of translations and dilations, or affine functions. Great. Okay, so if c is not equal to 0, c not equal to 0, if c is not equal to 0, I can scale the top and bottom by lambda, and we can assume without loss of generality that c is equal to 1. Think about that for a second, right? If c is not equal to 0, I'll multiply the top and bottom by what? I'll take the top and bottom and multiply by lambda, which is c inverse basically, and that won't change the function at all because that's multiplying by 1, but that will normalize c to 1. So we can assume without loss of generality that c is equal to 1. Okay, good? And so then what does your mapping look like? Your mapping looks like this. Then your mapping looks like, then your S of z is going to be a z plus b over d, right? Okay, and so what's the first thing we're going to do over here? So the first thing we're going to do is, I think we're going to do this. So let's think carefully about how we're going to do this. So let's do it slowly. So the first thing I'm going to do is I'm going to translate by d, right? So I'm going to do tz d is going to be what? It's going to be z plus d. And there's a z down here, right? Z plus d. Okay. Good. So that's z plus d. Then if I do inversion of that, so I'm going to do inversion of t dz. That becomes what? 1 over what? Z plus d. That's good. I've got our denominator by 2 compositions of a translation and inversion. Then here comes the only tricky part. I have to think about this. I need a b, and then I have to subtract off a and then d. So I need to dilate this by, the next step is to do dilation of b minus ad, like that, of this expression, of inversion of td of z. Will be what? Well, now, this is going to be, I'm going to scale this by b minus ad. So this is exactly equal to what? This is exactly b minus ad over z plus d. And then finally, the last step we're going to do, the last thing we're going to do is I'm going to shift by a. I'm going to do a translation by a of what? of dilation by B minus AD, then inversion, then TD of Z. So I have a translation, inversion, dilation, translation, okay? Is going to be what? Well, it's going to be this thing over here, B minus AD over Z plus D. Into that, I'm going to add A. So I'm going to write that as AZ plus D over what? Over Z plus D. And thank goodness I did that correctly, because now I have a what? I have an A and a Z, so I have an AZ on top. Then I have an AD and a negative AD. Those are going to cancel. And then I have a B, and then I have a what? Z plus D. And that's exactly what we started with over here. That's exactly equal to my S. So I've written S as a what? As a composition of a translation, a dilation, an inversion, and a translation over here, right? So what we've done is we've written a linear fractional transformation as a composition of a translation, dilation, and inversion. Now the next thing we'll do in the next video is we're going to say, okay, well, look at these first two geometric constructions over here. Translation takes lines and circles to lines and circles. Dilation takes lines and circles to lines and circles. So the question is, what does inversion do? Does inversion take lines and circles to lines and circles? In the next video, we'll see, yes, that we'll study inversion broadly, and we'll see that inversion maps lines and circles to lines and circles. So we'll prove that LFTs, via this decomposition over here, map lines and circles to lines and circles. Thank you very much.